One of the best ways to learn math is through examples. So the purpose of this video is to explore certain ways of solving differential equations through the lens of RLC circuits. Okay, so as a quick review for those who haven't seen circuits or just haven't seen them in a while, the R stands for resistor, C for capacitor, and the L for inductor. Yes, the L is for inductor to honor Lenz, who came up with Lenz's law, etc. To form the differential equations, we'll use these formulas. So the voltage across a resistor is measured by the current times the resistance. The capacitance is the charge over the voltage, which can be rearranged to say that the voltage across a capacitor is the charge over the capacitance. And lastly, the EMF, which can be rewritten as the voltage across the inductor, is the inductance times the change in current over time. Okay, now with the intro stuff out of the way, we can actually solve for differential equations using these methods listed right here. First, let's look at first-order ordinary linear differential equations. These ones are only going to contain a variable and its derivative, so you can solve these with RC circuits and LR circuits. So let's get into the separation of variables for RC circuits. So first we write Kirchhoff's loop rule, which is just the voltage across a whole loop equals the sum of the voltage across each of the components. And we can plug in the equations that we discussed on the previous slide right here, so we'll get that the EMF equals Q over C plus IR. Now we can identify the fact that I is just the derivative of Q, so we'll plug in dQ over dt instead of I, and then just use lowercase q for differentiating between what's a constant and what is a variable here. So this gives us our first differential equation of the video, and now we can solve it to get a function for Q with respect to t. So the whole point of separation of variables is that we are going to separate our variables that are dependent on Q and t separately and then integrate them. And since Q is really the only variable, you can write it in whatever form you would like, but it is common practice to get it in terms of this fraction, that we get a negative 1 over RC term on the dt side and the 1 over Q minus EMF times C on the dQ side. And to solve this, all we did was multiply by a common factor and then simplify until we got the numerator to be epsilon C minus Q over RC, and then we just divided the numerator epsilon C minus Q over to the other side and then multiply the dt on both sides. And here we're going to assume that time starts at t equals 0 and Q ranges from 0 to Q, which is just the maximum charge, to set the bounds of our integrals. So here we're just using U substitution to set U equal to Q minus epsilon C, and then we change our bounds accordingly. By solving that integral, we'll get natural log of Q minus epsilon C minus natural log of negative epsilon C, which can be condensed using the property of logs, and then both sides can be raised to the power of e to get rid of the natural log, and then we will be left with a factor e to the negative t over rc, and then we just use algebra to isolate q, and this gives us a function that q of t equals epsilon c times, in parentheses, 1 minus e to the negative t over rc. And just for fun, if you wanted to figure out a function for current, since we had current in our original differential equation, we can just take the derivative of the equation we just solved to get I of t equals epsilon over r times e to the negative t over rc. We can graph these as well to see and make sure that these kind of match what we expect the trends to be like. For q of t, we get this function right here, and this matches our predictions because the charge at the beginning is 0, and as the circuit keeps running, it reaches its maximum, which is epsilon times the capacitance, since it is charging the capacitor. And on the flip side, for the current in the system, it starts at its maximum, which is epsilon over r, and as we continue to charge the capacitor, less charge is going to be floating around, so at the end, when t approaches infinity, our current will approach 0. Awesome. Since we're on the topic of separation of variables, we can real quick look at LR circuits as well. Once again, we have our circuit with a battery and a resistor and an inductor, and we can use Kirchhoff's loop rule to write that the voltage difference is the voltage across the resistor plus the voltage across the inductor. And we substitute our equations, and this time we already have our derivative that the inductance is associated with di dt. So our variable that we're solving for this time is I, which is the current. And this gives us this differential equation, which we will solve in the same method as we did previously. The only difference is that instead of a 1 over c, we're using an L as one of the coefficients. So as you can see, once again, we separate the variables with di on one side and dt on the other. We take the integral, Once again, we're assuming that it starts at t equals 0 and ranges from 0 to maximum current, which is I. And we're once again left with a natural log, which we can use the same property. And then we isolate I to get e over r times parentheses 1 minus e to the negative r over L times t. And if we wanted to find the change in current as a function of time, we can just take the derivative of I and get di over dt equals epsilon over L times e to the negative r over L times t. These equations look similar to what we got for the RC circuit as well, because once we graph these, it's pretty much the same exact graphs. But this time the scenario is a bit different because our function is the current, which starts at 0 because the inductor is resisting the flow of current. And as time progresses or time approaches infinity, it's going to reach the maximum current it possibly can, which is the EMF divided by the resistance. Similarly, the inductance is going to start at its maximum, which is why di dt is going to be at its max, which is epsilon over L. And as time progresses and the current increases, the di dt is going to decrease and approach 0. Okay, now we look at the method using the integrating factor. And this time, let's just do both of these together since we kind of see the similarities between the two equations. Let's look at both of the circuits right here. So these were the differential equations that we created earlier. Let's put them in standard form, which just means that it's in the form of dy dt plus some coefficients or functions times y equals some other function. So as you can see right here, we have dq dt plus 1 over rcq equals epsilon over r, and on the other side we have di dt plus r over li equals epsilon over l. Let's call the coefficient or the functions associated with our y function p of t, and on the other side it equals m of t. Here you can see that the 1 over rc is the decay rate for the charge, also known as tau, which governs the dampening of the current in the system. We also have the decay rate, but for the current, which governs dampening of the current. And these two, m of t, are just the highest states that it would reach, as you might have seen in the graph from earlier. So let's look at the equations we solved for our y prime functions. As you can see, we basically have the equations in the form of m of t times e to the negative t times p of t, as the p of t function was the decay rate and the m of t function was just the maximum for our derivatives. Similarly, it's a bit harder to see in our y functions, but if you rewrite them like this, you can see that our equations for y of t were just m of t over p of t times 1 minus e to the negative t times p of t. And as you can see, the r's and the l's are canceling out in these equations to give us what we solved for earlier. So one benefit of putting it in standard form is that you can see patterns and you can see specific coefficients that might correlate to an envelope function or a decay rate or frequency when solving for differential equations. Okay, but since we're solving another method, let's just make it more fun by thinking of varying current rather than just EMF, which is a constant number. Here we'll just plug in delta V of t, which is just some voltage as a function of time. So the method of solving using an integrating factor is first we find an integrating factor. We call it mu of t, and this function with the e looks very similar to what we had last time. The only difference is that instead of negative t over rc, we have a positive one. But that's okay, we'll get to a similar equation very soon. Next, we take our mu of t and multiply each term of our differential equation by it. Here I'm multiplying it into the standard form, and as you can see on the left side, the mu of t times y prime of t plus mu of t times y, it kind of looks like the product rule, doesn't it? So instead of writing it, we can condense it and just pretend that, oh look, we just took the product rule of mu of t times y, and then that means that the other side just equals the derivative of whatever's in the bracket right here. So to solve for it, we can just integrate the right side with respect to dt, and we'll just solve for the mu of t times q of t, which we can divide over. So this gives us a standard form for varying current as a function of time. So if we had varying current, which was, let's say, sine of t, then we can solve this integral to get a new equation, which is a bit different from what we had previously. Okay, and just to confirm that we're getting the same result as we did for the separation of variable, let's pretend that delta v of t just equals some constant epsilon. So if we plug that in, we can factor this out, then we can take the derivative of e to the mu of t, and simplify, and we're left with a very similar equation as to last time, but we have a constant k. So all we do is we check the initial conditions like we did last time. So we have that q of 0 equals 0, and at the end, q max equals epsilon c. So if we plug that in, we can solve that k equals negative rc, and if we plug that in, we get the exact same equations we got last time. Same for LR circuits. We can just plug in our initial conditions, which is that initially when time equals 0, the current starts at 0 as well, and when we solve for it, we get the exact equation as well. Similarly, if we just use the integral definition that we came up with, we can just take the derivative to find I for RC circuits and di dt for LR circuits, and we're left with these functions right here. And if you would like, you can check the initial conditions and we get the exact same equations that we derived with separation of variables. So yay, both of these methods work. Now let's move on to second order ordinary linear differential equations, which just means that we're not just going up to y and y prime, we're going up to y plus y prime plus y double prime. So let's start it off with simple LC circuits. So in this scenario, we do not have a battery. We're starting off with a fully charged capacitor and an inductor. And this will just go back and forth charging and resisting each other. So we start off with Kirchhoff's loop rule, and since there is no battery, the EMF equals 0, which equals the voltage difference across the capacitor plus the voltage across the inductor. And we plug in the definitions like we got last time, and this time, since I is the derivative of Q, di dt is the second derivative of Q. So now we have our second order differential equation because we have a second order derivative right here. And once again, we're using little q to differentiate between what is a varying charge versus what is the final maximum charge. So our first method of solving is by using an auxiliary equation. So to write out the auxiliary equations, we're just going to replace our second derivative by r squared, our first derivative by r, and our actual y function by nothing. So we get a polynomial instead of a differential equations, which is LR squared plus 1 over c equals 0. Next, we solve for the roots of our auxiliary equation, also known as a characteristic polynomial. Since we know that L and C are constants that are greater than 0, we can just plug in these values right here and we're left with plus minus I over square root of LC. The thing to notice is when we have imaginary roots, the format we use is C1 cosine of beta t plus C2 sine of beta t, where alpha and beta are the imaginary and real components of a complex root. Okay, so we have C1 and C2, which are two values that we do not know, so it's probably a good idea to have two equations that we can use and solve for them using a system of equations. So let's just take the derivative of q to get a function for I of t. And here is what we get if we take the derivative using the chain rule. And let's set the initial values that the charge at time equals 0 starts at maximum because the capacitor is charged fully. And the current starts at 0 because initially there is no current flowing, and once it starts flowing, that is when we start the time of our function. Now we can just plug in the values and solve, and we get that C1 equals Q max and C2 equals 0. So basically we're getting rid of the sine term, and we're left with Q max cosine of 1 over square root of LC times t. And once again, you can take the derivative to get the function of current and the function of di dt as a function of time. Let's graph these. What does it look like? We just have sinusoidal functions which have different maximum and minimum ranges, or the amplitude. And this makes sense because what is happening in the system is that the capacitor is charged fully, then the current starts flowing, and then the inductor is like, no, we do not want this. And then all that happens is that the signs of the capacitor plate become from positive negative to negative positive. And it just goes and flips back and forth, which is why there's a negative part to Q maximum as well. Now that we have established ways of solving all of these other equations, we can finally move on to RLC circuits as a whole with all three components. In this scenario, we're just going to have a charged capacitor, a resistor, and an inductor. So similarly, we start off with 0 EMF because there is no battery, and we use Kirchhoff's loop rule to sum the voltage across all the different components in order. And once again, we can plug in the fact that Q equals Q, I equals dq dt, and di dt equals the second derivative of charge. Once again, we're writing the auxiliary equation as we did earlier, and since we know that all three of these coefficients are positive, these are the roots that we will be left with using the quadratic equation. Now, this one is a bit different from our previous scenario because this can produce three types of roots. First, we will have two distinct roots, which means that the plus and minus are going to produce two different numbers. If this expression is greater than 0, it will produce repeated roots if this expression is equal to 0, and it will produce complex roots if it's less than 0, the part inside the radical. So let's take it part by part. For the first scenario, where we have distinct roots, this is an overdamped system. So what this means is that the resistor is way too strong, that the back and forth between the L and C is not really creating much of a difference, and the system is just getting damped very fast. So the roots that we have are these two right here, and the format that we use for distinct roots is C1 times e to the power of root 1 times t plus C2 times e to the power of root 2 times t. So let's just plug in both of our roots. And this is the function that is generated, which aligns with what we predicted, that the current is just going to go down without much oscillation happening like we saw in the sinusoidal functions. In our second scenario, we have repeated roots, which means that somehow this factor of resistance is the exact same as the factor of 4 times L over C. So the two roots that we obtain are going to be negative R over 2L. This is a critically damped system, which just means that it's in some sort of equilibrium, in some sort of balance, that the oscillation is going to occur and it is slowly going to get dampened as well. So the format we use for repeated roots is C1 times e to the power of root times t plus C2 times t times e to the power of root times t. So once again, we're just plugging the values in. And one cool thing we can do here is that we can also make this an initial value problem and say that the system starts at t equals 0 at Q0 and ends at 0 current, because that is when the resistor is going to have dissipated all of the charge from the system. So if we solve for those, we can simplify this equation as so, and this is what the graph would look like. As you can see, it's kind of starting to produce a bit of a sinusoidal function, but is going down as a function of e as well, kind of like an envelope function. Lastly, we have our third option, which is producing complex roots. So the format here, as we discussed in the previous auxiliary equation, was C1 times e to the alpha t times cosine of beta t plus C2 times e to the alpha t times sine of beta t. Here, alpha is the coefficient corresponding to the imaginary part of the complex root, and beta is the real part of the complex root. So we can write this as such, and once again we can make this initial value problem and plug in that Q at time equals 0 is Q0 and current at times equals 0 is 0. So this way we get rid of the sine function, just to simplify the equation a bit so we can see more of the patterns. And this is the graph that it produces. As you can see, it's a cosine function, but it's being enveloped by an e to the negative r over 2l function right there. So what this basically means is that the cosine is the part that corresponds to the LC, which causes the oscillation back and forth, but the resistor is also resisting and dissipating some of that charge, so we have an overall exponentially decaying function as well, which all makes sense according to what we would expect from a circuit. So next, we move on to undetermined coefficients. This method is used when the right side of the equation also has a function attached to it instead of just equaling 0, which would have been the homogeneous case earlier. So since we already solved for the homogeneous solution, let's solve for the one particular solution where the charge that is going in is actually AC, which means alternating current. And here we're using E0 cosine omega t for that current. One thing to note here is that the frequency omega equals 1 over the square root of LC. So once again, we write our auxiliary equation. So to use this, we're going to look at our function on the left side, f of t, and it has to follow the layout of kt to the m times e to the alpha t times cosine beta t, or sine beta t. So we're going to recognize what each of these variables are. Since there is no numeric coefficient other than 1, k equals 1, no t to the power of anything, so m equals 0, no e to the power of anything, so alpha equals 0, and beta is just omega, which is, as we described earlier, 1 over the square root of LC. This is the same as the frequency that we got for LC circuit in our simple harmonic motion, which is important to note here. So let's move on to the roots of our auxiliary equation. We have the same three scenarios as last time. We have the overdamped case, the critically damped case, and the underdamped case. And one more thing to notice is that when we write a solution to undetermined coefficients, we're following the template y particular of t equals t to the s times a sub m times t to the m plus as many all the way down to a1 times t plus a naught and all times e to the pt. And to know what power of t to multiply by our polynomial, we have to see s. So, since we recognize what alpha and beta are, we can use those to write our complex number. And if that is one of the roots of our auxiliary equation, s equals 1, and if it's not, then s equals 0. So since alpha equals 0 and beta equals 1 over the square root of LC, that means our complex number here is 1 over square root of LCI. And since in the overdamped and critically damped cases, those are real numbers, they cannot be a root, therefore s equals 0. On the other hand, for the third case, for the underdamped case, there are complex roots, so there is a chance that it could either be a root or not be a root, depending on what the numbers end up being. So we have to think of both cases, where s equals 0 or s equals 1. So let's solve the first two cases first, since this time s equals 0, so our particular solution is going to be much easier. So we follow the format, as we listed earlier, t to the s, which is 0, times a sub m, which is also 0, so we just have a naught, times e to the alpha t, and since alpha is also 0, there's an e term. So this simply boils down to a naught cosine beta t plus b naught sine beta t. And beta, we're going to use omega in this case, because that is the value we were given earlier. Then we take the derivative, which you can do by using chain rule, and then we take a second derivative of that. Then we plug in these particular solutions into our differential equation. So for q double prime, q prime, and q of t, we plug in what we solved for right now. Then we can distribute the L, R, and 1 over c since they're constants, and group the terms by cosine and sine, and set them equal to e naught cosine of omega t. One thing to notice is that there's only a cosine omega t on the right side, so the coefficient attached to the cosine has to equal e naught, and the coefficients attached to the sine have to equal 0. This gives us a system of equations that we can solve to get the value of our two variables a naught and b naught. So here, all I did was I plugged in 1 over the square root of LC for omega, and this simplified the equations, giving us a naught equals 0 and b naught equals this. Therefore, we can just plug these values into what we solved for q particular, and then we get that qp of t equals epsilon naught over r omega times sine omega t. Next, as we discussed earlier about superposition, let's take the homogeneous solution we solved for earlier and the particular solution from now. The particular for both of these is the same, but the homogeneous one is different, and then we can just individually add it. Homogeneous particular equals this. And for the second scenario, the homogeneous plus the particular equals this. And once again, we can see that this is an overdamped system, as in the transient state, the graph goes very quickly to the 0, and then it oscillates back and forth, as you would expect from alternating current, which, as we described earlier, was just a cosine graph. Similarly, for a critically damped system, it starts off at a maximum, goes down, but not as fast, and the steady state is reached much faster, and the transient state is very short-lived in this scenario. And since we already have the particular solution for the scenario where s equals 0, we can also add it to our homogeneous solution for the third scenario, which is an underdamped system with complex roots. The only thing we have to know here is that this only occurs when the capacitance does not equal 4 times the inductance cubed, which means that 4 times L over C does not equal omega. That is not the frequency. And when that is the case, then we have s equals 0, and if we add the particular in the homogeneous solution, we're left with this equation. Let's look at the graph, and similarly here, as we would expect from an underdamped system, the oscillation starts, but the amplitude slowly decreases until it reaches a steady state, which is just the cosine graph for the AC. And lastly, for the undetermined coefficients, now we solve for the scenario where s equals 1, and this happens when the capacitance equals 4 times the inductance cubed, which means the frequency is 4 times L over C. The only difference here is that instead of our q particular being a naught cosine plus b naught sine, we have a naught times t times cosine plus b naught times t times sine. And the math works out pretty much similarly, but we have more terms to work out. And as you know, now we have to use the product rule to solve it. So first we take the derivative of qp, then we group our terms based on cosines and sines, then we take the derivative again, then we regroup our terms, and then we can plug it into the equation. This time, we regrouped the cosine terms on one side and the sine terms on one side. And there are many more terms this time because we had that extra t in there. Then we can group the three of these together because they seem to resemble the differential equation, and we can group the other one together. We can see that the expression attached to the cosine should equal E naught, and the one attached to the sine should equal 0. We once again get a system of equations. Now we can plug in the value for omega like last time, which is 1 over the square root of LC. This simplifies the equation quite a bit, and it allows us to solve with some simple algebra that A naught equals R E naught over R squared plus omega squared times 2L plus RT squared, and B naught equals E naught times omega times 2L plus RT over the same denominator. We can take this and plug in the values and factor out an E naught times T factor so that we do not have such a huge expression. Once again, we can use the principle of superposition and add the homogeneous and particular solutions together to get this kind of a monstrous looking equation, but it gets the job done. So in a scenario where the frequency is 4 times L over C, this is a graph we could expect. It starts off as a sinusoidal graph, as we would expect from AC current, and it increases a bit until it reaches steady state because this is an underdamped system, which means the resistor is not as powerful and is not dissipating the energy or the charge quite as fast. And the last method of solving differential equations is by using Laplace transforms. This one's kind of just fun because the whole point of using Laplace transforms is that you take a calculus problem with differential equations and you turn it into basic algebra by using properties and linearity of Laplace transforms. So one idea we're using here is that the Laplace of y prime equals s times the Laplace of y minus y of 0. So by using that, we can also find that Laplace of y double prime equals s squared times the Laplace of y minus s times y of 0 minus y prime of 0. And we use that for q double prime and q prime of t, and we plug the values right here. So first, in this, we're going to turn it into standard form by dividing all the terms by L, and then we use the definition of the Laplace of higher order derivatives, and we sub it into the equation. And then we set it equal to the Laplace of E naught of sine omega t. We can group our terms, which are the Laplace of q of t minus q prime of 0 minus the ones corresponding to the q of 0. And this all equals E naught times omega over s squared plus omega squared, which is how you take the Laplace of a sine function. Here it is important to know the initial values, and since we're using AC with a sign, we can say that the charge at the beginning is 0, in which we're saying that the capacitor does not hold any charge, and the current is also 0, which means that the current has not started flowing through our circuit yet. Then we can plug these in for q prime of 0 and q of 0, and it simplifies to this. Then we can divide over the polynomial next to the Laplace of q of t onto the other side. This can then be expanded to be written as such, and the reason we're doing this is because we are trying to get this algebraic equation to look like something whose Laplace we already know, so that we can take the inverse Laplace later. So since it's getting a little complicated, we can define new variables. Let's call lambda equal to r over 2L, and alpha equals to the square root of omega squared minus lambda squared, which, if we plug in the values, is just the square root of 1 over LC minus r squared over 2L, assuming that omega is greater than or equal to lambda. So if we substitute those values in right there, this equation doesn't look that bad. Now we have to use partial fraction decomposition to get it in terms of an equation that looks like this. A1 times s plus lambda plus b1 times alpha over s plus lambda squared plus alpha squared plus a2 times s plus b2 times omega over s squared plus omega squared. If we can get our equation in this format, we can use the format of the Laplace of e to the something times sine or cosine of something. So we find the common denominator and multiply the denominator by the opposite terms, and then we set it equal to 1 because in our equation on the left we have 1 equals the format that we are trying to get our equation into. Now, one way to solve for these 4 unknown values is that we can just expand this out into a polynomial of third degree, and if we do so, we'll end up getting coefficients that correspond to s cubed, s squared, s, and s to the 0, which is 1. That gives us a system of 4 linear equations which we can use a matrix to solve. So this matrix right here, which corresponds to A1, B1, A2, and B2, and it equals 0, 0, 0, and 1. Since on the left side, our equation equals 0, and it doesn't have a s cubed squared or s factor to it, all of the first three equations equal 0 and the last one equals 1. And we can use an augmented matrix to reduce it down to this, which gives us these values for the 4 terms. Now we can plug in b2 to the 3 that are dependent on b2 in order to expand them out as such. As you can note, lambda squared plus alpha squared minus omega squared equals lambda squared plus omega squared minus lambda squared minus omega squared, which just ends up canceling out and becomes 0. So we can cancel these terms out, and after more algebraic manipulation, we are left with a sub 1 equals 1 over 2 lambda omega squared, b1 equals 1 over 2 alpha omega squared, a2 equals negative 1 over 2 lambda omega squared, and b2 simply equals 0. Which might look like simple numbers, but let's not forget that we have defined the 3 variables as such. However, for the purposes of finding a solution, we can now plug these values into our model equation for a1, b1, a2, and b2. And once again, we can simplify them a bit, factoring out a 1 over 2 omega squared from all the terms, and we're left with simpler terms inside. We can simplify that a bit more, and now we're ready to take the inverse Laplace of our algebraic equation. From the first part, we can factor out a 1 over lambda, which is just a coefficient, and take the inverse Laplace of s plus lambda all over s plus lambda squared plus alpha squared. This will equal e to the negative lambda t times cosine of alpha t. Then for the second term, we can factor out a 1 over alpha, and we're left with the inverse Laplace of alpha over s plus lambda squared plus alpha squared. This will become e to the negative lambda t times sine of alpha t. And lastly, we can factor out 1 over lambda. We're left with s over s squared plus omega squared, and this is just a sine of omega. And if we combine these as such, we're left with q of t equals this not that bad looking expression. And now we can once again graph this, and as you can see, we get a graph that looks very similar to the graph we got for s equals 1 scenario for our underdamped system, but this time it's a sine graph, so it starts off small and increases until it reaches steady state. And these are all the methods of solving differential equations we're going to cover in this video.